let's talk about Io, which is the moon of Jupiter.
Right.
Okay, it's like epic. There's like volcanoes all over the place. It's from a distance, it's awesome. So can you tell me about this moon? And you're sort of a scholar of many planets and moons, but that one kind of stood out to me. So why is that an interesting one?
For so many reasons, but Io is the most volcanically active object in the solar system. It has hundreds of active volcanoes on it. It has volcanic plumes that go hundreds of kilometers up above its surface. It puts out more volume of magma per volcano than volcanoes on Earth today. But I think, to me, the reason that it's most interesting is as a laboratory for understanding planetary processes. So one of the broad goals of planetary science is to put together a sort of more general and coherent framework for how planets work in general. Our current framework, it started out very Earth-centric. We start to understand how Earth volcanoes work. But then when you try to transport that to somewhere like Io that doesn't have an atmosphere, which makes has a very tenuous atmosphere, which makes a big difference for how the magma degasses. For something that's really small, for something that has a different heat source, for something that's embedded in another object's magnetic field, the kind of intuition we have from Earth doesn't apply. And so broadly, planetary science is trying to broaden that framework so that you have a kind of narrative that all you can understand how each planet became different from every other planet. And I'm already making a mistake. When I say planet, I mean planets and moons. Like I said, I see the moons as planets.
As planets. Yeah, I actually already noticed that you didn't introduce Io as a moon of Jupiter. You completely you kind of ignored the fact that Jupiter exists. It's like, let's focus on the yeah. Okay, so and you also didn't mention Europa, which I think is is that the most famous moon of Jupiter? Is like the one gets attention because it might have life.
Exactly. Yeah.
Okay. But to you, Io is also beautiful. What's the difference between volcanoes on Io versus Earth? You said atmosphere makes a difference. What?
The heat source plays a big role. So, many of the moons in the outer solar system are heated from gravitationally by tidal heating, and I'm happy to describe what that is.
Well, yeah,
or
please.
not.
What's
Okay.
tidal? Yes.
So tidal
Yes, please.
heating it's if you want to understand and contextualize planets and moons, you have to understand their heat sources. So for Earth, we have radioactive decay in our interior as well as residual heat of formation. But for satellites, tidal heating plays a really significant role, and in particular in driving geological activity on satellites and potentially making those subsurface oceans in places like Europa and Enceladus habitable. And so the way that works is if you have multiple moons and their orbital periods are integer multiples of one another, that means that they're always encountering each other at the same point in the orbit. So if they were on just random orbits, they'd be encountering each other at random places, and the gravitational effect between the two moons would be canceling out over time. But because they're always meeting each other at the same point in the orbit, those gravitational interactions add up coherently. And so that tweaks them into eccentric orbits.
What's an eccentric orbit?
So eccentric orbit or elliptical orbit, it just means non-circular, so a deviation from a circular orbit. And that means that, for Io or Europa, at some points in their orbit, they're closer to Jupiter, and at some points in their orbit, they're farther away. And so when they're closer, they're stretched out in a sense, but literally just not very stretched out, like a couple hundred meters, something like that. And then when they're farthest away, they're less stretched out. And so you actually have the shape of the object deforming over the course of the orbit. And these orbits are like just a couple of days. And so that, in the case of Io, that is literally sufficient friction in its mantle to melt the rock of its mantle. And that's what generates the magma.
That's the source of the magma. Okay, so why is Europa is, I thought there was like ice and oceans underneath kind of thing. So why is Europa not getting the friction?
It is. It's just a little bit farther away from Jupiter. And then Ganymede is also in the orbital resonance. So it's a three-object orbital resonance in the Jupiter system. But we have these sorts of orbital resonances all over the solar system and also in exoplanets. So for Europa, basically because it's farther from Jupiter, the effect is not as extreme, but you do still have heat generated in its interior in this way, and that may be could be driving hydrothermal activity at the base of its ocean, which obviously would be a really valuable thing for life.
Cool. So it's like heating up the ocean a little bit.
Heating up the ocean a little bit, and specifically in these like hydrothermal vents where we see really interesting life evolve in the bottom of Earth's oceans.
That's cool. Okay, so what's Io? What else? So we know the source is this friction, but there's no atmosphere. I'm trying to get a sense of what it's like if you and I were to visit Io. Like, what would that look like? What would it feel like? Is this the entire thing covered in basically volcanoes?
So it's interesting because there's very little atmosphere. The surface is actually really cold, very far below freezing on the surface when you're away from a volcano. But the volcanoes themselves are over 1,000 degrees, or the magma when it comes out is over 1,000 degrees, and so.
But it does come to the surface, the magma.
It does, yeah.
In particular places. Whoa, that probably looks beautiful. So it's frozen, not ice. Like, what is rock? It's really cold rock, and then you just have this like what does that look? What would that look like with no atmosphere? Would it be smoke? What does it look like? It's just magma, like just red, yellow, like liquidy things.
It's black. It's black and red, I guess. Like, think of the type of magma that you see in Hawaii. So different types of magma flow in different ways, for example. So in somewhere like Io, the magma is really hot, and so it will flow out in sheets because it has really low viscosity. And I think the lava flows that we've been having in Hawaii over the past couple of years are probably a decent analogy, although Io's magma's lavas are even more fluid and faster moving.
How faster? Like what? How fast? Like if you? By the way, sorry. Through the telescope, are you tracking at what time scale? Like every frame is how far apart? If you're looking through a telescope, are we talking about seconds? Or are we talking about days, months? When you kind of try to get a picture of what the surface might look like, what's the frequency?
So it depends a little bit on what you want to do. Ideally every night, but you could take a frame every second and see how things are changing. The problem with that is that for things to change on a 1 second time scale, to actually see something change that fast, you have to have super high resolution. The spatial resolution we have is a couple hundred kilometers, and so things are not changing on those scales over 1 second unless you have something really crazy happening.
So if you get a telescope closer to Io, if you get or a camera closer to Io, would you be able to understand something? Is that something of interest to you? Would you be able to understand something deeper about these volcanic eruptions and how magma flows and just the rate of the magma? Or is it basically enough to have the kilometer resolution? Do you get a sense?
No way. We want to go there.
You want to go? You want to go to Io?
I mean, I don't want to go there personally, but I want to send a spacecraft mission there. Absolutely.
Why? Why are you scared?
Why am I scared?
Oh, you mean you don't?
I don't want to go there as a human.
As a human,
I want to send a robot there to look at it, though.
This is again, everybody's discriminating against robots. This is not, but it's fine. But it's not hospitable to humans in any way, right? So it's very cold and very hot.
It's very cold. The atmosphere is composed of sulfur dioxide, so you can breathe it. There's no pressure. I mean, it's kind of all the same things you talk about. One talks about Mars, only worse. The atmosphere is still 1,000 times less dense than Mars's. And the radiation environment is terrible because you're embedded deep within Jupiter's magnetic field. And Jupiter's magnetic field is full of charged particles that have all come out of Io's volcanoes, actually. So Jupiter's magnetic field strips all this material out of Io's atmosphere, and that populates its entire magnetosphere, and then that material comes back around and hits Io and spreads throughout the system. Actually, it's like Io is the massive polluter of the Jupiter system.
Okay, cool. So what does studying Io teach you about volcanoes on Earth, or vice versa? Is in the difference of the two? What insights can you mine out that might be interesting in some way?
Yeah, we try to port the tools that we use to study Earth volcanism to Io, and it works to some extent, but it is challenging because the situations are so different and the compositions are really different. When you talk about outgassing, Earth volcanoes outgas primarily water and carbon dioxide, and then sulfur dioxide is the third most abundant gas.
Mm-hmm.
And on Io, the water and carbon dioxide are not there.
Right.
Either it didn't form with them or it lost them. We don't know. And so the chemistry of how the magma outgasses is completely different. But the kind of one, to me, most interesting analogy to Earth is that so Io, as I've said, it has these really low viscosity magmas. The lava spreads really quickly across its surface. It can put out massive volumes of magma in relatively short periods of time. And that sort of volcanism is not happening anywhere else in the solar system today. But literally every terrestrial planet and the moon had this, what we call very effusive volcanism early in their history.
Okay, so this is almost like a little glimpse into the early history of Earth.
Yeah.
Okay, cool. So, what are the chances that a volcano on Earth destroys all of human civilization? Maybe I wanted to sneak in that question.
Yeah, a volcano on Earth.
Do you think about that kind of stuff when you just study volcanoes elsewhere? Because isn't it kind of humbling to see something so powerful and so hot, like so unpleasant for humans? And then you realize we're sitting on many of them here.
Right. Yeah, Yellowstone as a classic example. I don't know what the chances are of that happening. My intuition would be that the chances of that are lower than the chances of us getting wiped out by some other means.
Okay.
That in the time, that maybe
Comforting.
it'll happen eventually, that there'll be one of these massive volcanoes on Earth, but we'll probably be gone by then by some other means. Not to sound bleak, but
it's very comforting.